The summer air over Brandenburg shimmers with heat as Hauptmann Werner Thierfelder walks toward the fighter, sitting on Rechlin's concrete apron. It's the 20th of July, 1944, and the aircraft before him shouldn't exist here. The olive-drab paint is scratched and faded. Someone has crudely brushed Luftwaffe crosses over where American stars once proclaimed their allegiance. But no amount of paint can disguise what this machine represents. He circles the P-51D Mustang slowly, methodically, the way a predator might assess unfamiliar prey, or the way prey might study its predator. The fuselage is narrower than he expected, almost delicate compared to the robust Focke-Wulfs he's accustomed to flying. His hand runs along the wing's leading edge, feeling the smoothness of the laminar flow surface that German engineers have heard about but never successfully replicated in production. The aluminum skin feels thin, almost fragile. American manufacturing philosophy, he thinks. Build it light, build it fast, build 10,000 of them. For 4 years, Werner Thierfelder has served the Luftwaffe, first as a fighter pilot flying intercept missions against RAF bombers over the Ruhr, later as a test pilot at this secretive facility north of Berlin. He has flown captured Soviet Yaks that were handled like tractors with wings. He has tested British Spitfires that turned beautifully but ran out of fuel embarrassingly quickly. He has evaluated the American P-47 Thunderbolt, a massive radial engine fighter that German pilots nicknamed the Jug for its resemblance to a milk jug powerful in a dive, but lacking the agility for sustained dogfighting. But this aircraft is different. The reports filtering back from the Western Front have been increasingly urgent, increasingly troubling. Luftwaffe pilots are encountering a fighter that seems to violate the fundamental constraints of aviation engineering. A long-range escort fighter shouldn't be possible. According to German aerodynamic theory, the fuel weight required for extended range should make the aircraft too heavy for competitive performance. Yet the Americans are somehow escorting their heavy bomber formations all the way to Berlin and back, and the fighter providing that escort is outperforming Germany's best interceptors in combat. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Mustang was forced down near Aachen 2 weeks ago, its Packard-built Merlin engine coughing and failing after what the pilot reported as a fuel contamination problem. He belly landed in a field, the aircraft sliding to a halt largely intact. Wehrmacht ground forces secured it before the pilot could destroy it. Within hours, it was being transported eastward, away from the advancing front lines, toward Rechlin. Thierfelder's orders are straightforward. Evaluate the aircraft's performance characteristics, identify its strengths and weaknesses, and determine whether the combat reports are accurate or exaggerated. Find something German pilots can exploit. He climbs onto the wing and slides into the cockpit. The seat position is immediately notable, set higher than in German fighters, providing exceptional visibility. The canopy is a bubble design, a single piece of curved plexiglass with no framework interrupting the view. He can see in nearly every direction. In a Messerschmitt Bf 109, the heavy canopy frame creates significant blind spots. Here, there are none. The instrument panel spreads before him, labelled in English. Someone has added small strips of paper with German translations: manifold pressure, fuel mixture, coolant temperature. The layout is logical, everything within easy reach. American ergonomics, he notes. They design for the pilot rather than designing the pilot to fit the aircraft. He studies the throttle quadrant. The throttle itself is on the left side, which will take adjustment. German fighters place it on the right. But the positioning seems natural once his hand finds it. Below the throttle, the mixture control and propeller pitch lever. The Americans use a constant speed propeller, automatically adjusting blade angle to maintain optimal RPM. Another example of their philosophy: automate what can be automated so the pilot can focus on fighting. The technical specifications have been meticulously documented by Rechlin's engineering staff over the past week. The Packard V16507 engine, essentially a license-built Rolls-Royce Merlin 61, produces 1,490 horsepower at war emergency power with water methanol injection. The two-stage, two-speed Supercharger maintains power output at altitudes where German engines begin to struggle. The propeller is a Hamilton standard four-blade unit, 11 feet in diameter. Weight empty, 7,040 pounds. Maximum takeoff weight, 12,100 pounds. That's with full internal fuel and ammunition. Add 2 external drop tanks and the weight increases to over 14,000 pounds, yet combat reports indicate the aircraft remains maneuverable even with this burden. The armament is purely gun-based. 6 Browning M250 caliber machine guns, 3 in each wing. No cannons, unlike German practice. The Americans have chosen volume of fire over hitting power, gambling that 50 caliber rounds striking at a high rate will accomplish what a few cannon shells might miss. In combat, Luftwaffe pilots report that the Mustang's guns are devastatingly effective, particularly in deflection shooting, where the high rate of fire creates a cone of bullets through which an enemy aircraft must pass. Thierfelder signals to the ground crew. They move to their positions around the aircraft, chocks ready, fire extinguisher at hand. No one is entirely certain this American engine will start reliably with German fuel and German maintenance. The Merlin is notoriously particular about fuel quality. It requires high-octane gasoline that Germany can no longer produce in sufficient quantities. They're using captured American fuel for this test, stockpiled from overrun supply dumps in France. He follows the startup procedure that's been translated and posted in the cockpit. Fuel mixture rich. The throttle cracked open 1 inch. Magnetos to both. His thumb finds the starter button. The engine turns over once, twice, catches. The four-blade propeller begins to rotate, slowly at first, then spinning into an invisible disc. The Merlin's distinctive sound fills the air, a deep, smooth rumble, fundamentally different from the harsher mechanical snarl of a Daimler-Benz DB 605. There's a refined quality to it, an impression of precision manufacturing and careful tolerances. The British designed this engine in the 1930s as a racing power plant, then adapted it for the Spitfire. The Americans took the design, improved the manufacturing process, and produced it in quantities that German industry cannot match. Tens of thousands of Merlins have been built. They power not only the Mustang but also the P-51's British predecessor, the legendary Spitfire, as well as the heavy Lancaster bomber. It is perhaps the war's most successful aircraft engine, and it isn't German. This troubles Thierfelder more than he cares to admit. He has been raised on the mythology of German technical superiority. The Reich's propaganda apparatus has spent years cultivating the image of German engineering as the world's finest. The early victories of 1940 and 1941 seem to confirm this narrative. German tanks overran Poland and France. The Luftwaffe swept aside the Polish Air Force and severely damaged the French. Even the vaunted RAF was fought to a standstill over Britain, or so the official version claims. But 1944 tells a different story. The Luftwaffe is losing pilots faster than they can be trained. Aircraft production is actually increasing. Factories are churning out Messerschmitts and Fokker-Wulfs in record numbers, yet German fighters are being destroyed faster than they can be replaced. Not because of manufacturing capacity, but because of the quality gap in both machines and pilots. American pilots arrive over Germany with 200 to 300 hours of flight training. German pilots now receive 30 to 50 hours before being thrust into combat. The Americans fly aircraft that seem to violate the supposed laws of aeronautical engineering. The Germans fly refined versions of designs from 1939, incremental improvements on obsolescent concepts. Thierfelder begins his taxi, steering the Mustang toward Rechlin's main runway. The tail wheel is steerable, linked to the rudder pedals, providing precise ground control. Visibility over the nose is adequate, better than in the Bf-109 with its narrow-track landing gear and nose-high attitude, though not quite as good as in the Fokker-Wulf 190's wide-stance configuration. He performs his pre-takeoff checks, flight controls free and correct, trim tabs set for takeoff. Fuel selector main tank, mixture rich, propeller full forward, flaps up for takeoff. The Americans don't use flaps for normal takeoff runs, relying instead on the wing's inherent lift characteristics. The tower clears him for departure. He turns onto the runway, aligns the nose with the center line, and advances the throttle smoothly forward. The acceleration is immediate and authoritative. The Merlin's power pushes him back into the seat as the Mustang surges down the concrete. The tail comes up quickly, improving visibility dramatically. Airspeed indicator climbing. 100 km per hour, 150, 200. At 220 km per hour, Thierfelder eases back on the stick and the Mustang lifts cleanly into the air. The runway falls away beneath him. 400 meters of takeoff roll. His Focke-Wulf 190 typically requires 600 meters. Already an advantage. Gear up. The landing gear retracts into the wings with a solid thunk and the characteristic rumble of mechanical systems doing their work. And then, immediately, viscerally, Thierfelder feels something unexpected. The Mustang accelerates as if it has been released from restraints. There is no laboring against drag, no sense of the aircraft struggling to convert power into speed. It simply goes. The airspeed needle climbs steadily. 250, 300, 350 kilometers per hour. He's barely at 1,500 meters altitude, and already the Mustang is moving faster than many German fighters at their maximum velocity. The aircraft climbs out over the Brandenburg countryside, passing through 2,000 meters, 2,500. Thierfelder makes small inputs to the controls, feeling the Mustang's responses. The ailerons are light but effective. He can bank the aircraft with minimal effort. The elevator is smooth, progressive, no tendency toward pitch sensitivity or over-control. The rudder requires little input even in climbing flight. The engine's torque is well balanced. This is an aircraft designed for long-duration missions, he realizes. Everything about the handling suggests an emphasis on pilot comfort and reduced fatigue. A German fighter demands constant attention, constant small corrections. The Mustang seems content to fly itself, while the pilot attends to navigation, formation keeping, or scanning for enemies. At 3,000 meters, he levels off and begins systematic evaluation. Gentle turns to the left, to the right, steeper banks. The Mustang responds predictably, progressively. There are no bad habits, no tendencies toward snap rolls or spins. It is, he thinks, almost boringly stable, which is exactly what you want for a fighter that must escort bombers through hours of flight into hostile territory. Then he opens the throttle to maximum continuous power and pushes forward slightly on the stick, transitioning into level acceleration. The response is extraordinary. The airspeed indicator climbs with unsettling rapidity. 350 kilometers per hour, 400, 450, 500. The Mustang is still accelerating. 550, 600, 650. At 4,500 meters altitude, the aircraft reaches 715 kilometers per hour, approximately 444 miles per hour in the American measurement system. Thierfelder has flown the Focke-Wulf 190A8, one of Germany's premier fighters, considered among the best interceptors available to the Luftwaffe. That aircraft achieves a maximum speed of approximately 653 kilometers per hour at optimal altitude. The Messerschmitt Bf 109G, which forms the backbone of German fighter wings, can barely exceed 621 kilometers per hour under ideal conditions. This American fighter is not marginally faster. It is faster in a way that fundamentally alters the tactical equation of air combat. A 60 km per hour speed advantage means a German pilot cannot catch a fleeing Mustang, cannot escape a pursuing Mustang, cannot dictate the terms of engagement. The American pilot chooses when to fight and when to disengage. The German pilot has no choice but to accept whatever the Mustang pilot decides. 4 years of war have taught Thierfelder that speed in combat aviation isn't just about going fast, it's about controlling the engagement. The faster aircraft decides whether combat occurs. In fighter versus fighter combat, this is decisive. He pushes the nose down and begins a climb test, advancing the throttle to war emergency power. The water methanol injection system activates, feeding a mixture into the supercharger to prevent detonation and allowing the engine to produce maximum output. The Merlin's roar deepens as it generates its full 1,490 horsepower. The Mustang climbs strongly through 5,000 meters, 6,000. German fighters begin to lose performance at these altitudes as their single-stage superchargers struggle to compress the thinning air. The Mustang's two-stage supercharger, a masterpiece of British engineering refined by American manufacturing, maintains power output 7,000 meters, 8,000. At altitudes where Messerschmitts become sluggish and unresponsive, where Focke-Wulfs labor to maintain speed, the Mustang feels entirely comfortable. The controls remain effective. The engine produces smooth, reliable power. This is the aircraft's element. 9,000 meters, 10,000. At 10,000 meters, 32,800 feet, the Mustang is still climbing at over 4 meters per second. The official service ceiling is listed as 12,770 meters, but Thierfelder suspects the aircraft could go higher if he asked it to. This explains everything. The combat reports aren't exaggerated. They're probably understated. American heavy bombers operate at 7,000 to 8,000 meters altitude, where German flak is less effective and where oxygen deprivation affects German fighter pilots, who often have inadequate equipment. The Mustang escorts operate above the bombers, between 9,000 and 11,000 meters, where they can dive down onto any Luftwaffe interceptors, climbing to attack. German pilots must climb through the bomber formations, through the concentrated defensive fire of hundreds of 50-caliber machine guns, then engage the fighters at an altitude where their own aircraft are struggling for performance, while the Mustangs are operating in their optimal envelope. It isn't a fair fight. It was never designed to be a fair fight. Thierfelder levels off at 8,000 meters and begins a series of maneuverability tests. He rolls the Mustang left, then right, evaluating aileron response at altitude. The controls remain crisp, responsive. He pulls into a climbing turn, feeling the gee forces press him into the seat. The aircraft holds the turn without wallowing or sliding. He reverses, rolling right and pulling hard. The Mustang responds immediately, transitioning smoothly from one high G turn to another. This is where he expects to find the weakness. Long-range fighters traditionally sacrifice maneuverability for endurance. The additional fuel weight, the aerodynamic compromises necessary for extended range, these should make the aircraft less competitive in a turning fight. The Spitfire turns beautifully but carries fuel for barely 2 hours of combat. The American P-47 Thunderbolt has excellent range, but fights like the heavy aircraft it is, relying on speed and diving attacks rather than sustained turning engagements. The Mustang seems to ignore this supposed dichotomy. It turns with authority. Not quite as tightly as a Bf-109 at low altitude, the German fighter's light wing loading gives it an advantage in pure turn radius, but far better than any long-range fighter that has a right to turn. And at altitude, where the thin air reduces the effectiveness of the 109's small wing, the Mustang's larger wing area provides superior lift. Up here, above 7,000 meters, the Mustang might actually outturn a Messerschmitt. He continues the evaluation, methodically documenting the aircraft's handling characteristics at various speeds and altitudes. Slow flight, stable, with adequate stall warning through buffeting. The stall itself is benign, with no tendency toward wing drop or spin entry. Recovery is straightforward. Relax back pressure, add power, regain flying speed. High-speed handling. The aircraft remains stable and controllable. No flutter, no excessive vibration. The controls become heavier at high speed, requiring more force, but remain progressive and predictable. This is good design heavy. Controls prevent the pilot from overstressing the airframe with abrupt inputs at velocities where structural limits become critical. Now for the test that will reveal the most. High-speed diving characteristics. German fighters have a troubled relationship with diving attacks. The Bf-109, in particular, suffers from compressibility problems at high speed. As the aircraft approaches the speed of sound, which is lower at altitude due to the cold temperatures, The airflow over the wings and control surfaces begins to reach transonic velocities. Shock waves form. The controls become unresponsive or lock up entirely. The aircraft enters a condition where the pilot cannot recover, tumbling toward Earth until either the dive flattens at lower altitude, where the speed of sound is higher, or the aircraft disintegrates under aerodynamic loads. Luftwaffe pilots have died this way. Training emphasizes caution in high-speed dives. Engage, attack, but do not pursue a diving enemy beyond certain velocity limits. Thierfelder points the Mustang's nose downward, 15 degrees below the horizon, 20, 30 degrees. He advances the throttle, adding power to the dive. The airspeed indicator begins its climb. 500 kilometers per hour, 550, 600. The aircraft remains stable, tracking straight down its flight path. 650, 700. He steepens the dive to 45 degrees. The ground below green Brandenburg farmland, cross-hatched with roads and villages, grows larger in the windscreen. 750 kilometers per hour, 800. The controls remain responsive. He can feel pressure on the stick, the aerodynamic forces resisting his inputs, but the ailerons and elevator continue to function. There is no buffeting, no sense of impending structural failure. The Mustang is diving at over 800 kilometers per hour, approaching 500 miles per hour, and it feels controlled, almost routine. At 800, 5 kilometers per hour, Thierfelder pulls back firmly on the stick. The aircraft responds immediately. The nose rises. The G-forces build 3G, 4G, pressing him down into the seat, greying his vision at the edges. The dive flattens, transitions to level flight, then into a climb. The Mustang sheds speed rapidly, trading velocity for altitude, and settles into level flight at 4,000 meters. No structural complaints, no control problems, no surprises. This is the piece that completes the tactical picture. A Luftwaffe pilot who attempts to escape a Mustang by diving will not escape. The Mustang can follow him down, remain controlled at speeds where German fighters become unresponsive, and still have the power to climb back up afterward. There is no safe escape vector except perhaps a very low-altitude dash where ground proximity might deter pursuit, but even that is doubtful given the Mustang's excellent visibility and handling characteristics. Every tactical option German pilots have relied upon for 4 years of air combat speed, altitude, diving attacks has been nullified by this single aircraft design. Thierfelder begins his descent back toward Rechlin, throttling back to conserve fuel. The Mustang still carries nearly 70% of its internal fuel after 40 minutes of aggressive flight testing, including multiple climbs to high altitude and high-speed runs. The fuel management is extraordinary. The internal tanks hold 1,100 pounds of fuel, about 170 gallons. Add 2 external drop tanks of 110 gallons each, and the total fuel load reaches 390 gallons. The numbers translate to a combat radius of approximately 750 miles with drop tanks. The Mustang can fly from England to Berlin, a distance of nearly 600 miles, escort bombers over the target, engage in combat, and return to England. No German fighter can make this claim. The Bf-109G has a combat radius of approximately 200 miles. The TEM-5 190A manages perhaps 320 miles with a drop tank. German fighters must operate close to their bases. They scramble, climb to intercept altitude, engage the bombers, land to refuel and rearm. If they are drawn away from their bases by American escorts, they must break off combat to reach their airfields before fuel exhaustion. The Americans suffer no such constraint. They can remain over German territory for hours, always present, always a threat. The strategic implications are devastating. He enters the landing pattern at Rechlin, reduces power, and extends the landing gear. The Mustang slows to approach speed smoothly. Flaps down the aircraft's nose, pitches down slightly, requiring a small back pressure on the stick to maintain the glide path. Over the runway threshold, throttle to idle, gentle back pressure. The main wheels kiss the concrete, the tail settles, and the Mustang rolls out straight and true. 47 minutes of flight time. 47 minutes that have fundamentally altered Thierfelder's understanding of the air war. He taxis back to the dispersal area where ground crew and engineers wait. As he shuts down the engine, the Merlin winding down with a decreasing whine, he organizes his thoughts. The report he will file must be precise, technical, and honest. The Luftwaffe High Command needs accurate information, not comforting falsehoods. But there is another dimension to what he has just experienced, something that transcends technical specifications and performance data. He has just flown an aircraft that represents a comprehensive refutation of everything German aviation doctrine assumes about long-range fighter design. The Rechlin facility has been testing captured Allied aircraft since the war began. Early Soviet fighters were crude but effective. British Spitfires were impressive but limited by short range. American P-47 Thunderbolts were powerful but heavy. Each aircraft had clear strengths and identifiable weaknesses that German fighters could exploit. The P-51D Mustang has strengths in every category and no exploitable weaknesses. It is faster than German fighters at all altitudes. It climbs better above 6,000 meters. It dives better at all speeds. It turns adequately for combat. It has a range that makes German fighters look like training aircraft. It has better visibility than any Luftwaffe fighter. It has reliable systems and an engine that produces smooth, predictable power. And this is perhaps the most psychologically difficult aspect. It is not produced in small numbers by master craftsmen in specialized workshops. It is mass-produced in American factories by semi-skilled workers, thousands of aircraft rolling off assembly lines at a rate German industry cannot begin to match. Over the following 3 days, Thierfelder and his team compile their formal evaluation report. The document is methodical, organized, and damning. Performance summary. Maximum speed at 4,500 meters, 715 kilometers per hour. Service ceiling, 12,770 meters. Rate of climb at sea level, 16.3 meters per second. Combat radius with drop tanks, 1,210 kilometers. Endurance at cruise power, 4 hours 15 minutes. Comparative analysis. Against Focke-Wulf 190A8, the Mustang is faster at all altitudes, climbs better above 6,000 meters, dives better, and has triple the combat radius. The Fu 190 retains advantage in roll rate at low altitude and has heavier armament with cannon. Overall assessment. Mustang superior in most combat scenarios. Against Messerschmitt Bf 109G6. The Mustang is faster at all altitudes, climbs better above 5,000 meters, dives significantly better, and has triple the combat radius. The Bf 109 retains advantage in sustained turn rate at low altitude and has comparable armament. Overall assessment. Mustang superior in most combat scenarios. Tactical implications. The P-51D represents a fundamental shift in fighter design philosophy. German fighters prioritize heavy armament, robust construction, and competitive performance in the European theater's typical combat envelope of 3,000 to 6,000 meters altitude. The Mustang achieves its performance through aerodynamic efficiency, an exceptional engine matched to an optimized airframe, and revolutionary laminar flow wing design that reduces drag. Most significantly, the aircraft's range allows it to escort American heavy bombers to any target in German-controlled territory. Luftwaffe fighter pilots can no longer wait for bomber escorts to reach their fuel limits and turn back. The escorts never turn back. The report includes technical appendices, detailed photographs of the laminar flow wing construction, analysis of the Supercharger system, documentation of the fuel management arrangement, examination of the armament installation. German engineers study every aspect of the design, looking for insights that might be applied to Luftwaffe aircraft. But here is the bitter truth that the report cannot explicitly state. Even if German designers could replicate every feature of the Mustang's design tomorrow, Germany lacks the industrial capacity, the raw materials, and the time to produce such an aircraft in meaningful numbers. The Mustang's Packard Merlin engine requires high-octane fuel that Germany cannot synthesize in sufficient quantities. The Reich's synthetic fuel production is already under heavy bombing attack. By autumn of 1944, German fighters will be grounded not because they lack aircraft, but because they lack fuel to fly them. The Mustang's construction uses aluminum alloys that Germany must import or synthesize at great expense. American industry produces aluminum in quantities that dwarf German output. A single Mustang requires approximately 1,000 hours of labor to construct. American factories are producing them at a rate of more than 400 per month. German fighter production, despite heroic efforts, struggles to replace combat losses. And even if Germany could build a Mustang equivalent, there are no pilots to fly them. Luftwaffe training programs have collapsed under the dual pressure of fuel shortages and the need to feed replacement pilots to frontline units. New German fighter pilots receive 30 to 50 hours of flight training before being sent into combat. Their American opponents have 200 to 300 hours of training, much of it in aircraft closely resembling what they will fly in combat. The Americans are not just winning the technological race, they are winning the industrial war, the resource war, and the training war. They are winning every dimension of the conflict simultaneously. Thierfelder's report makes its way through Luftwaffe bureaucracy, stamped and forwarded up the chain of command. It reaches the headquarters of Jagdkorps, the fighter command. It is read by staff officers responsible for tactics and doctrine. It is noted, filed, and ultimately archived. What the report cannot change is the fundamental strategic situation. By July of 1944, the Luftwaffe was fighting a defensive war it could not win. The invasion of Normandy has succeeded despite German air opposition. Allied fighters and bombers operate over German territory with increasing impunity. The carefully constructed Luftwaffe fighter defense system, radar stations, ground controllers, regional fighter wings, is being systematically dismantled by overwhelming force. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The test flight at Rechlin is merely confirming what combat statistics already prove. In the month of July 1944 alone, the Luftwaffe lost approximately 450 fighter pilots killed, missing, or captured, a catastrophic attrition rate that pilot training programs cannot replace. American losses are also significant, but American training schools are producing pilots faster than they are being lost. German training produces pilots slower than they are dying. The Mustang is not simply a better fighter aircraft. It is the visible manifestation of American, industrial, technological, and organizational superiority. It is proof that the United States can design, produce, and field a weapon system that surpasses German equipment, while simultaneously producing that system in quantities that make German production look trivial. On the 25th of July, 1944, 5 days after Thierfelder's test flight, the captured Mustang was flown again, this time by a different pilot who wanted to verify the findings. The results are identical. The aircraft performs exactly as documented. There are no surprises, no hidden weaknesses to exploit. The Mustang sits at Rechlin through August and into September, occasionally flown, frequently studied. German engineers photograph every detail, measure every dimension, analyze every aspect of its construction. They learn much about American design, philosophy, and manufacturing techniques, but they cannot replicate it. Not with the resources available, not with the time remaining. By October of 1944, Allied forces had liberated France and were approaching Germany's western border. The Rechlin facility, once secure deep inside German territory, is now within range of Allied fighters conducting armed reconnaissance missions. The captured aircraft collection, including the Mustang, must be evacuated further east or destroyed to prevent recapture. The specific fate of the captured P-51D tested by Thierfelder is not conclusively documented. Most likely, it was destroyed in place as Soviet forces approached Brandenburg in the spring of 1945. Possibly it was abandoned when Rechlin was evacuated, left sitting on a dispersal hardstand as German personnel fled westward. Perhaps it was damaged beyond repair during an Allied air raid and scrapped for metal. Whatever its end, the aircraft disappears from history in the chaos of Germany's collapse. Werner Thierfelder survives the war. He was captured by American forces in May of 1945 and spent several months in a prisoner of war camp before being released. In post-war interviews conducted by Allied intelligence officers debriefing Luftwaffe test pilots, he speaks candidly about his experiences at Rechlin and his assessment of Allied aircraft. When asked specifically about the P-51D Mustang, his response is unequivocal. It was the finest all-around fighter of the war, superior to the Focke-Wulf 190, superior to the Messerschmitt 109, superior even to Germany's jet-powered Me 262 inches most practical combat scenarios, because the Mustang was reliable, available in quantity, and could be flown by moderately trained pilots with confidence. This admission must have been psychologically difficult for a man trained in the mythology of German technical supremacy. But Thierfelder was, above all, a test pilot, a profession that demands intellectual honesty and the ability to report unpleasant truths. His evaluation of the Mustang was not influenced by national pride or ideological loyalty. It was the product of 47 minutes in the cockpit of an aircraft that redefined what a fighter could be. The story of German test pilots flying a captured Mustang and acknowledging its superiority is not simply an anecdote about aircraft performance specifications. It represents a profound collision between ideology and engineering reality, between propaganda and measurable truth. The Third Reich constructed much of its identity around claims of technical and industrial supremacy. German engineering was presented not merely as excellent but as inherently superior, a manifestation of racial and cultural characteristics that made German technology fundamentally better than what other nations could produce. This was not just marketing aimed at foreign audiences. It was internal propaganda that Germans themselves were taught to believe. The Luftwaffe's early successes seemed to confirm this narrative. In 1939 and 1940, German fighters dominated Polish and French opposition. The Messerschmitt Bf 109 was genuinely world-class in this period, faster, better armed, and more advanced than most opposing fighters. The Luftwaffe's tactical doctrine, emphasizing coordinated attacks and radio communication between aircraft, was innovative and effective. But the Battle of Britain revealed the first cracks in this mythology. The Supermarine Spitfire proved to be the Bf 109's equal in performance and superior in certain aspects of handling. British pilots, fighting over their own territory with the advantage of radar early warning, inflicted unsustainable losses on the Luftwaffe. The planned invasion of Britain was postponed indefinitely. Still, the narrative of German technical superiority could be maintained. The Bf 109 was upgraded with more powerful engines. The Focke-Wulf 190, introduced in 1941, was genuinely superior to the Spitfire Mark V then in RAF service. German industry was producing excellent aircraft in substantial numbers. What changed between 1941 and 1944 was not a sudden German technological decline. German fighters continued to improve incrementally. The Bf 109G was faster and better armed than the Bf 109E that fought over Britain. The W190 was continuously refined with more powerful engines and improved systems. What changed was the nature of the opposition. The Soviet Union began producing fighters in enormous quantities, aircraft that were often crude but effective, and available in numbers that made German victory through attrition impossible. The Yakovlev Yak-3, introduced in 1943, was lighter and more maneuverable than German fighters at low altitude. The Lavochkin La-5FN matched the performance of contemporary German fighters and was produced by the thousands. The United States brought to bear an industrial capacity that dwarfed German production. American factories produced over 96,000 fighters during the war years. German production totaled approximately 55,000 fighters across all types. This disparity would be significant even if the aircraft were of comparable quality. But American aircraft were not merely numerous. They were, by 1943 and 1944, technically superior to German designs in most categories. The P-51 Mustang represents the culmination of this technical evolution. It was not the first American fighter, nor even the first good American fighter. It was the synthesis of multiple technological streams: British aerodynamic research into laminar flow wings, British engine design in the Rolls-Royce Merlin, American manufacturing expertise in mass production of complex systems, and American operational experience defining requirements for a long-range escort fighter. North American Aviation began designing the Mustang in 1940, initially for British use. The first prototype flew in October of that year, a remarkably short development timeline of just 120 days from contract to first flight. This rapid development was possible because North Americans drew on existing knowledge rather than attempting revolutionary innovation. The laminar flow wing was based on NACA research. The airframe structure used conventional aluminum construction. The engine was an existing British design that Packard was already manufacturing under license. The original Mustang, powered by an Allison engine, was fast at low altitude but lacked high-altitude performance. It served effectively in ground attack and reconnaissance roles, but was not a competitive air, superiority fighter. The breakthrough came when someone accounts differ on who first suggested it, proposed installing the Merlin engine in place of the Allison. The combination was transformative. The Merlin's two-stage supercharger maintained power at high altitude, where the Allison struggled. Suddenly, the Mustang became not just fast, but fast at all altitudes. The P-51B, first flying in December of 1942, demonstrated performance that exceeded all existing fighters. The P-51D, with its bubble canopy and increased ammunition capacity, refined the design further. By mid-1944, when Thierfelder flew the captured example at Rechlin, the Mustang was being produced at a rate of over 400 aircraft per month. Total P-51 production would eventually exceed 15,000 aircraft, nearly equal to the total production of all Focke-Wulf 190 variants throughout the entire war. This industrial capacity was itself a weapon. Even if German fighters achieved favorable kill ratios in individual engagements, and by late 1944 they often did, not the mathematics of attrition favored the Allies overwhelmingly. The Americans could lose aircraft and replace them within weeks. The Germans could not. But the captured Mustang at Rechlin forced German test pilots to confront something more psychologically difficult than simple numerical inferiority. They had to acknowledge that the American aircraft was not just more numerous, but genuinely better. Better in ways that could be objectively measured and could not be explained away through excuses about pilot training or tactical circumstances. The Mustang was faster. This could be verified on a stopwatch. It climbed better at high altitude. This could be measured with an altimeter and timer. It had a longer range. This could be calculated from fuel consumption rates. It was handled well. This could be felt directly through the control stick. Every measurement, every test, every objective evaluation reached the same conclusion. The Americans had out-engineered Germany in the design of this aircraft. This was not supposed to be possible, according to Nazi racial ideology. Americans were depicted in German propaganda as culturally inferior, their society weakened by democracy and racial diversity. How could such a nation produce technology superior to that of the racially pure, disciplined, organized German Reich? The cognitive dissonance must have been profound for true believers. For pragmatists like Thierfelder, the evidence was simply evidence uncomfortable perhaps, but undeniable. The test flights at Rechlin were not the only instances of Germans flying captured Mustangs. Several P-51 seconds were forced down or captured relatively intact during the war. Each was eagerly studied. The conclusions were always the same. In one documented case, a Luftwaffe pilot who had flown both the Bf-109 and the captured Mustang described the experience as like comparing a Volkswagen to a Mercedes. This was perhaps unfair to the Messerschmitt, which was an excellent fighter by the standards of 1939. But by 1944, the 109 was a refined version of an obsolescent design, continually upgraded to remain competitive but fundamentally constrained by its original configuration. The Mustang, by contrast, was a clean-sheet design, incorporating the latest aerodynamic understanding and optimized for the specific mission of long-range escort. It had no legacy constraints, no compromises made to accommodate pre-war assumptions. It was what a fighter could be when designed with perfect information about what the war actually required. German engineers studying the captured Mustang were particularly interested in the laminar flow wing. This design, developed by NACA, the National Advisory Committee for Aeronautics, predecessor to NASA, maintained smooth airflow over a greater percentage of the wing surface, reducing drag significantly. In theory, German designers understood laminar flow. In practice, they had never successfully implemented it in a production fighter. The manufacturing tolerances required were extremely tight. Any surface imperfections, any rivet heads protruding above the skin, any paint texture, roughness, would disrupt the laminar flow and negate the benefits. American manufacturing achieved these tolerances reliably in mass production. German manufacturing, for all its reputation for precision, could not match this consistency at scale. The Mustang's wing was a triumph not just of design but of industrial process control. This pattern repeated across multiple systems. The Packard Merlin engine was not inherently better than German engines in terms of fundamental design, but American manufacturing quality control ensured that each engine performed to specification reliably. German engines of the same period showed greater variation in performance between individual examples. Some were excellent, others were marginal. The Americans delivered consistency. The Mustang's fuel system was another revelation. The aircraft carried fuel in multiple tanks, fuselage tanks, wing tanks, and external drop tanks. A sophisticated fuel management system allowed the pilot to balance fuel consumption to maintain proper center of gravity throughout the flight. The tanks were self-sealing, lined with rubber that would swell when punctured by bullets, closing small holes and preventing catastrophic fuel loss. German fighters had self-sealing tanks too, but the American implementation was more robust. More importantly, the sheer quantity of fuel the Mustang could carry while maintaining excellent performance demonstrated a level of design integration that German engineers admired but could not replicate given the constraints they faced. Even small details revealed the thought put into the Mustang's design. The cockpit layout was logical and uncluttered. The gun sight was simple and effective. The radio equipment was reliable and easy to use. The landing gear was robust and tolerant of rough field operations. These seem like minor points, but collectively they represent the difference between a good aircraft and a great one. German fighters often excelled in raw performance, but suffered from reliability issues, complex maintenance requirements, or design quirks that made them difficult to fly. The Bf-109's narrow landing gear made ground handling treacherous. More pilots were lost to landing accidents than to some types of combat. The few 190's BMW radial engine was powerful but temperamental, requiring careful management to avoid overheating. The Mustang was, by all accounts, a pilot's airplane. It was forgiving of mistakes, reliable in operation, and effective across a wide range of combat scenarios. These qualities made it suitable for the realities of wartime operations where pilots varied widely in skill level and where aircraft could not receive perfect maintenance. By autumn of 1944, the Mustang had achieved what German aviation planners once believed impossible: true air superiority over Germany itself. American fighters patrolled German skies with impunity. Luftwaffe fighters, when they managed to get airborne despite chronic fuel shortages, were hunted ruthlessly by Mustangs that could outperform them in virtually every scenario. The German response was increasingly desperate. The Messerschmitt Me 262 jet fighter, when it finally entered service in significant numbers in autumn 1944, was faster than the Mustang, capable of over 850 km per hour. In pure speed, it represented a technological leap beyond propeller-driven fighters. But the Me 262 arrived too late and in too few numbers. Total production was approximately 1,400 aircraft. Many never flew combat missions due to fuel shortages, lack of trained pilots, or Allied bombing of airfields. The jet engines were temperamental, with service lives measured in hours rather than the hundreds of hours a Merlin engine could operate reliably. The Me 262 required long concrete runways for takeoff and landing, making it vulnerable to Allied fighters that would loiter near known jet bases and attack the Me 262 seconds when they were most vulnerable during takeoff and landing, when their speed advantage was negated. More fundamentally, the Me-262 represented a tactical dead end for Germany. Even if produced in unlimited quantities, even if perfectly reliable, it would not change the strategic situation. Germany was losing the war not because it lacked sufficiently fast fighters, but because it lacked fuel, trained pilots, functioning industry, and defensible territory. The Mustang and other Allied aircraft were not just winning air battles, they were destroying the infrastructure that made German resistance possible. American and British heavy bombers, escorted by Mustangs, systematically destroyed German synthetic fuel production. By early 1945, the Luftwaffe was effectively grounded not because aircraft were unavailable, but because there was no fuel to fly them. Hundreds of fighters sat on airfields, unable to take off. Pilots walked away from operational aircraft because there was no point in staying. The sophisticated technology, the advanced designs, the accumulated expertise of German aviation, all rendered irrelevant by the simple absence of fuel. This was the ultimate irony that Thierfelder's test flight foreshadowed. Germany had focused enormous resources on developing advanced fighters, continually refining the Bf-109 and Fw-190, developing the revolutionary Me-262, pursuing numerous experimental designs. But the Americans had pursued a different strategy. Build a very good fighter, build it in overwhelming numbers, use it to enable strategic bombing that would destroy the enemy's ability to fight. The Mustang was not the most advanced fighter of World War II in terms of raw technology. The Me-262 was faster. The Soviet Yak-3 turned tighter at low altitude. The British Spitfire Mark 17 had certain handling advantages. But the Mustang was the most effective fighter because it combined good enough performance with excellent reliability, outstanding range, and most importantly, availability in numbers that made strategic impact possible. This is a lesson that extends beyond World War II aviation. Technology competitions are not won simply by achieving the highest performance in individual systems. They are won by achieving sufficient performance in systems that can be produced reliably, maintained effectively, and employed at scale. The Germans pursued perfection in individual aircraft design. The Americans pursued adequacy at an overwhelming scale. When Thierfelder landed the captured Mustang at Rechlin after 47 minutes of flight testing, he possessed information that German leadership desperately needed. He had verified that the combat reports were accurate. The Mustang was indeed as good as Luftwaffe pilots claimed. In fact, it was probably better, because combat reports are always contaminated by confusion, fear, and incomplete observation. Test flying provided clinical, objective data, but information without the capacity to respond is simply another form of defeat. The Luftwaffe could not build a Mustang equivalent, could not train enough pilots to crew existing fighters, could not produce enough fuel to keep those fighters airborne, could not defend the industry that produced fighters from systematic destruction. Knowing you are losing is not the same as being able to prevent loss. The captured Mustang at Rechlin became a symbol, though probably not one recognized at the time, of the gap between German assumptions and Allied realities. It sat on a German airfield, wearing Luftwaffe crosses, but it remained fundamentally American. The paint did not change its performance. The markings did not alter its capabilities. It was what it was, evidence of American industrial and technological achievement that exceeded German capabilities. In post-war analyses of World War II aviation, historians and engineers have extensively studied the Mustang's design and its impact on the air war. The consensus is clear. The P-51D was one of the most important aircraft of the war, arguably the single most important Allied fighter in the European theatre. Its introduction in large numbers in early 1944 coincided with the collapse of effective Luftwaffe opposition. This was not a coincidence. The aircraft enabled the strategic bombing campaign that destroyed German industry. It achieved air superiority over Germany, making ground operations in France and later Germany itself possible without effective German air interference. It forced the Luftwaffe into a defensive posture from which it could never escape. And it did all this while being fundamentally simpler and cheaper to produce than many German fighters. The Mustang required approximately 25,000 man-hours to manufacture. A Focke-Wulf 190 required approximately 13,000 man-hours, but the Mustang was more capable, so the American investment paid better returns. When you factored in the Mustang's superior reliability and longer service life, the economic advantage became overwhelming. This economic dimension is often overlooked in discussions of military technology, but it was decisive. Wars are not won by the side with the best equipment. They are won by the side that can produce good enough equipment to sustain operations while denying the enemy the capacity to do the same. The Mustang was good enough to win air superiority while being cheap enough to produce in decisive quantities. For the German test pilots at Rechlin, this lesson was delivered viscerally, undeniably, through the experience of flying an enemy aircraft that outperformed their own. The intellectual understanding that Germany was losing, the air war became physical reality through the control stick of a captured Mustang. Werner Thierfelder continued his work as a test pilot through the final months of the war, evaluating new German aircraft as they became available and training pilots on the capabilities and limitations of Allied equipment. By early 1945, this work had become largely academic. There was little fuel, fewer pilots, and no realistic prospect of reversing German fortunes through aviation technology. He witnessed the evacuation of Rechlin as Soviet forces approached. The carefully maintained test facility, the accumulated technical knowledge, the captured aircraft collection, all abandoned or destroyed to prevent capture. The Mustang he had flown disappeared in this chaos, likely destroyed in place or possibly damaged beyond repair and left as scrap. After the war, Thierfelder participated in debriefings with Allied intelligence officers who were compiling comprehensive assessments of German aviation programs. These interviews produced a remarkable body of technical literature, as German pilots and engineers candidly discussed their experiences and acknowledged Allied technical achievements. The ideological constraints of the Nazi period were lifted. Men could speak honestly about what they had experienced. The consensus among Luftwaffe test pilots was striking in its consistency. The P-51D Mustang was the finest all-around fighter aircraft of World War II. Some German pilots continued to argue that specific German aircraft had advantages. In particular scenarios, the Fu-190D9 could dive faster. The Me-262 was obviously much faster in level flight, and the Bf-109K-4 climbed better at very low altitude. But when evaluated across all performance categories and all combat scenarios, the Mustang stood supreme. This admission represented a complete reversal of the narrative German pilots had been taught. They had entered the war believing German aviation was inherently superior. They ended the war acknowledging that an American aircraft designed in 1940, refined over several years, and produced in massive quantities, was better than anything Germany fielded. The psychological journey from one position to the other must have been disorienting. But for men like Thierfelder, trained in the discipline of test flying, where objective measurement superseded propaganda, the evidence was incontrovertible. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.